we working with here? 2. So this is only going to take you a minute longer if you're not finished yet. So your first step was to take your percentages and make them decimals, so 0.982 and 0.018, your 2 percentages, and then you multiplied by the actual mass that it's related to. So the 52 one is the 98.2, which is you're going to multiply by the full out mass versus the rounded version, just so we don't have any rounding error. And then the 0.181 is the 51, which is 50.996 AMU. Okay, so what do you guys get for the first one? Depending on you, I don't have my calculator here. First one. Any takers? Lindsay, what you got? I think it should be like 50 something. Give me a couple. 51.28. 28.49. Oh, I'm 5. Sorry, I didn't know you were doing that. I'm gonna stop there. So that's AMUs. Okay, what's the second one? 9? 0.9. Okay. 0.9. Say again. That sounds great. Okay. Okay, so we have 51, blah, 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 0.9, blah, 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 blah. And then, so first step was convert your percents decimal step. Second step is to multiply, which I've done here. Third step is to take these and add them together. That is it. And then tell me what you guys' summation is. 202. 52.202. And we have, let's see here. These are usually what we're looking for sig figs, because they are measurements. They're measurements of the mass of the atoms. The other ones are percentages. Percents are not measurements necessarily, so we ignore them in sig figs. So there are 5 sig figs there, 5 sig figs here. We're doing great. 3 decimals, also doing great. AMUs. All right, look at chromium on the PTOE. Find chromium is in the middle. And tell me what it's supposedly its average atomic mass is on the PTOE. 52.00. Okay, looks like we're doing pretty good, pretty close here. Okay, assuming that I got good numbers. Yeah. And I would refer this to fit as 52 as 2 sig figs. Most of the time, I'll tell you the isotope as like the mass notation, and then the actual like legit mass, most specific. All right, does that help you on any questions you had on PS4? Because I think that was really the only one that you guys may have had concerns about. Are there any other questions on PS4? We've had it for like 3 days, so I'm hoping that you ask me before anything you need to. Yeah.
3 on like the 16, 17. 3 on. But you're at the bottom.
Oh, is that the one with the identity of the like your naming and element of the theory?
No.
Here, let's go over the bottom then. What was your number again?
3.
Number 3 on the matching.
I don't know. I think I might have done it.
Is it on the matching? Democritus? Is your matching? I'm sorry, I just don't remember. Oh, is it C on that last one?
Yeah.
Okay, perfect. Number 5. That one?
3.
Oh no, that's what we just did. That's I'm assuming that if I have demonstrated how to do taking percents, multiplying by the specifics, and then adding up that final isotopes. This one, you have 3 isotopes of silicon and their average masses. So same process. Okay.
I didn't know if the answers at the bottom of the thing or 4 of those.
Should be 3 points. Number, what did you guys get for number 3 on the bottom? Oh, I got 28.09. Would you get 0.1, so 28-ish AMUs based off what you multiply by? Or 0.1. I got 0.9 for some reason, but it should be close to 28-ish AMUs. Okay, how about a non-isotope one? Anything else on matching those? Okay, I'll take them up for now, and I'll get them back to you, and we'll check over these, because I just want to see what you guys have done. Because we have a topic today that's kind of our brand new topic. We're out of isotopes and put in atomic particles, subatomic particles for now. We are going to really hone in on the interactions of light and matter, and then we're going to jump into electrons a bit more tomorrow. Yes, tomorrow. No, we'll jump into electrons. Thank you. Yes, fours. Thank you. So let's actually introduce by watching a video. So there are a couple of concepts, and I gave you guys back your reading guides 5 so that you could have some vocabulary in front of you because you've already defined these terms. But one of the terms on the back were Heisenberg's uncertainty principle. Do you remember that one? Particle wave duality. Yes, wavelength, frequency, energy. We're going to be kind of pulling all these together. Who's ever watched Minute Physics? Yes? Okay. They have some really hilarious videos, and they're like a minute each. So we're going to watch a couple of these first. Let me turn off Pandora. And then we'll jump into the actual new information. I have so many. Okay, there it is. So let's talk about light first. I'll put the lights down there.
Albert Einstein published a series of papers many consider a starting point for the modern age of physics. Rather than E equals mc squared, most people only know that Einstein was famous, not for what he was famous. Since this week marks the 125th anniversary of his birth, as is customary in Western tradition, we will celebrate by taking a brief tour of his scientific publications. Today, his paper from March 1905 on why light is a particle. Einstein didn't just pull this idea out of thin air. He first noted that the light emitted.
He said light is a particle. Light goes like this, and hits you in the face, and it bounces off things, right? We call that a wave, correct? A wave that kind of has wavelength to it. But he's saying light is a particle, meaning it has mass and it can interact with other matter. Let's see why.
Something hot, like a light bulb filament, actually has the same energy distribution as a gas, which is somewhat surprising if you're a 19th century physicist who thinks that light is a continuous wave and very much not a gas composed of individual molecules. And while the idea that light behaved kind of like a gas was already well known before Einstein, no one had taken the logical but crazy next step to conclude that light must then be made of individual particles too. So Einstein proposed that these light quanta were in fact real particles that could account for a few recent and unexplained experiments having to do with knocking electrons off of metals and gas molecules.
What is that called when light knocks electrons out of metals? We talked about yesterday, say it again? It's quantizing. That actually means it has energy. It was photoelectric effect, right? So he's saying, so he was trying to confirm the photoelectric effect, meaning that the photons in the light have enough energy and the ability to interact with matter, giving them particle wave dualities. So it's like almost like an alternate personality. Okay, it acts as a wave and it acts as a particle.
He turned out to be right on all counts and got a Nobel Prize for his work. But that's a story for another day.
Okay, so a little bit more on the particle wave duality. Let's look at the particle wave. Well, this will work. This will be photoelectric effect first. This one's very exciting. Okay, this guy on a simulation.
Photoelectric effect describes the effect caused when electromagnetic waves hit a metal surface, which can cause electrons to be released from the metal surface. These electromagnetic waves can be thought of as photons. Photons are small packets of energy which hit the metal surface. Each one has the potential of releasing an electron.
So right now it's just white light.
If we decrease the wavelength of these photons, this has the effect of increasing its frequency, which also has the effect of increasing.
So he said if we decrease the wavelength, it does what to the frequency? Increases. So would you say that's a direct or an indirect relationship? Direct means increased wavelength, increased frequency. They're opposites. It's called indirect, okay? And that is, I don't know if you can see this or not right here. That is a part of what we're going to talk about today, which is the you remember the lambda thing, the upside down like broom looking thing? That is lambda, that is wavelength. B, which is frequency, is they kind of complete each other to meet this constant, the speed of light, 3.00 times 10 to the 8 meters per second. So the C has to stay constant. So if wavelength goes up, somebody's got to go down to keep that C a constant value. So they are actually indirectly related, and we'll see how that affects the metal here as he indicates a little bit more.
The energy of these photons. You'll notice that as we get to a certain point, electrons start to be released from the metal surface.
That's
As that
because
continues to increase their energy, the electron's energy also increases.
so that's just because the different colored lights, the different wavelengths of light carry different energies with them. So again, can you tell me which is the most energetic form of light, red light or violet light? Did you guys see where the electrons started coming out when he got to like violet, maybe? So that means it's giving a lot of energy to the metal and it's pushing the electrons out. So thinking about that, where is the wavelength of violet light short or long? Very short, right? Very short. So is its frequency high or low? High. So really short wavelength moves really, really fast. And if it's moving very fast, its energy is very high. So you'll see there's a common variable between these two equations. We're going to be using this quite a bit. The frequency, as it's higher, the energy is also higher. And you'll notice that there's this another constant called the Planck constant at H. And that's another constant that needs to stay the same. So these actually are directly related, whereas these are indirectly related. So that's kind of what we're digging into today. Got one more video first, though. So Heisenberg's uncertainty principle talks about how with matter, sometimes we cannot pinpoint exactly where an electron is within an atom, within the greater scheme of the atomic model. So it's related to kind of what we're talking about today, but more than anything, it's just kind of blow your mind.
It's weird, right? But did you know that some of its supposed peculiarities are not unique to quantum physics, but are just properties of waves in general? Take the uncertainty principle. It says that the better we know where a particle is, the less we know about how fast it's going. There's a limit to how much we can know. But this isn't just quantum weirdness. It happens all the time with normal everyday waves. Remember that the frequency of a wave is how close the wave crests are to each other. A low-frequency wave doesn't have nearly as much oomph as a high-frequency one. And the position of a wave is, well, where the wave is, mostly. So where exactly is a wave? It's spread out everywhere, right? Okay, but for a wave pulse, it's pretty easy to see where the wave is. So now that we know where the pulse is, what's its frequency? Well, a localized pulse doesn't really wave, so we can't measure the frequency of its crests. And that's the uncertainty principle in a nutshell. You can either know where a wave is or where it's going, but not both at the same time.
And that's the same thing with the electrons. So my joke for you is Heisenberg and Einstein, or Heisenberg and any other scientist, they're riding down the road. Whoop, whoop. Police car pulls them over. Has anybody heard this? Okay. And so the police officer goes, "Sir, do you know how fast you're going?" They're like, "No." They 110 miles an hour. Dang it, now we're lost. Because they can either know how fast they're going or know where they are. They're not ready. Oh, okay, so that's we're going to dig into the background theories of mechanical quantum mechanics a little bit, but that's going to be something that is very complex, that will be related more so to Schrodinger's model. Okay, so this right here, I did not print this for you guys. I'm so sorry. I printed your isotope one, not this one. So I want you to do what you want in terms of definitions, because you have some reading guide 5 already. I'm going to put the lights back on so you don't. We're going to do a couple calculations with the speed of light, finding the wavelength of a particular color wavelength of light, and its speed. So we just need to be familiar with the terminology. And so the first one is the two that we most often reference are frequency and wavelength. Amplitude is not one we reference a lot, but you should know that it's related to how bright something is. So I'm going to say kind of how bright. And specifically for your frequency and your wavelength, write down these symbols, because that's what I will usually write from now on for those particular terms. So right now we're digging into the waves, to the electromagnetic spectrum, and the energy, different types of energy that make up the electromagnetic spectrum. So the wavelength, and you can see this picture up here that helps you. The wavelength is just the difference of the two heights of the crest of the wave. So we call that wavelength. And if I'm standing in one location, I can count how many wavelengths it has in a specific amount of time, and that would be called the frequency of the wave. So how fast is it passing a particular point? And that has multiple ways to denote the units. The most common ones are per second, like this, so 1/2, or second to the -1, or hertz. Valentine's Day is coming up. You guys have seen, maybe. What is love? Like what? What? Baby, don't hurt me. Don't hurt. Okay, I'll pull that up for you later. Okay, so frequency is going to be referencing kind of time. It's going to be referencing time quite a bit. So maybe your frequency, your speed this morning, was so many revolutions of your time, or so RPMs per minute. We're going to talk about waves passing per second usually. And then write down your speed of light. Speed of light is 3.0 times 10 to the 8th meters per second. And that is a constant, meaning it does not change. The speed of light is the speed of all energy in terms of meters per second, because all energy will travel at that speed, but the wavelengths and frequencies of that energy will change. So we are going to really talk about visible light first. And visible light has a narrow range of wavelengths that they take on. Because once things get too long and too fast, or too long and too slow, or too short and too fast, we can't see them anymore. Our photoreceptors and eyes, they just don't detect those types of wavelengths. So we can hear them, we can feel them, we interact with that type of energy in a different way. Sometimes it's so energetic it burns us. It can harm us. So like UV. We all have probably had a sunburn at one point in time. So we're going to be calculating different forms of energy, and I have the electromagnetic spectrum on the next slide. But the ones we're really worried about is visible light, because that's what we interact with more on a daily basis. Okay. So this is the electromagnetic spectrum. I didn't pass these out. Let me show you this. You have access to this online. After our table, you'll get from me. Look on the back side, you'll see the Bohr model. The Bohr model has this underneath. You don't necessarily need to memorize it. You just need to know where it is. You need to understand the relationships between the spectrum of different waves. You guys see on the bottom of the Bohr model, it's on the lower right, left-hand corner. Lower left-hand corner. Okay, so is yours written from gamma to radio, or is it radio to gamma? Okay, this is the way I memorized it. I made up a stupid mnemonic device to help me with that. But gamma rays are incredibly small. They're meters, 10 to the -14th meters. Radio waves are very large, 10 to the 4th meters. How many meters tall am I? How many feet tall am I, do you think? Okay, 5, 7.5. Let's be real. Okay, so let's call me 6 feet tall. Meters about 3 feet. So I'm about 2 meters tall. Okay, a radio wave is 10 to the 4th meters. Holy cow! We hear those things, right? That's what we set our radio stations to, so that it tunes in and it captures the waves and then sends it to us in hearable form. Okay, so that's really neat. Then we see, you can see. We see in this general region, and it's about 10 to the -5th, 10 to the -7th meters, but we don't talk about them in meters all the time. We usually do talk about them in nanometers, and that's why on the little chart there, it gives it to you in both nanometers and meters. So around the 700, 750 nanometer range is going to be your darkest red, or your last bit of wavelength of red. And over here at the 400 nanometer range, you're going to have violet. And so you can see that violet is much shorter, but it's also much faster. And faster meaning it has a high frequency. This one's going to be a high wavelength, but a low frequency. So it's going to be inversely related. This is the low wavelength, or a short wavelength. Okay, so since we're focusing on light now, I want you guys to tell me how we can use this formula to solve for one variable given the other one. What is the frequency? So what am I looking for? What variable? V. So what V is violet, or sorry, what is frequency of violet light at 400 nanometers? All right, so we know that we're given this. This is our given. Wavelength is 400 nanometers. What other variable do I always know? You wrote it down. C, speed of light. 3.00 times 10 to the 8th meters per second. Oh, what did I just say? Meters. So if I say meters, and I notice I'm in nanometers, I need to transition between them so I can actually use this. So the first step I need to do is take this to meters so I can import it to the speed of light formula. So you guys are writing down this example. I'm only going to do a couple, and you're going to want these, okay? For 400 nanometers. What are you thinking in your head right now that you probably want to write down? King Henry died by drinking chocolate milk, ... What's next? Say again? Micro, nano, pico. Good. Okay, so nano is way over here. Meter is here at base. If meter is here at base, nano is over here. What are you going to do? You're going to write here. Sorry, I'm going to try to switch one in here. I want meters on top because I want nanometers on bottom because I need to cancel this out. Which one gets the 1? Meter gets the 1. How many nanos are in a meter? Say again? Hold on. 10 to the... So there's a 1 there, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. A billion, right? So 10 to the 9th? Okay, nano 9, 10 to the 9th. You don't have to count it out every time. Just write 10 to the 9th. Okay, that'll help expedite your process. So, in your calculator, if you want to, or you can take this and do this in your head, you should get 4.0 times 10 to the negative 7 meters. Okay, so that's our official wavelength. And so the hard part in your calculator is just making sure that your calculator understands this is in the denominator. So I recommend using parentheses. So 400 divided by parentheses 10 to the 9th parentheses. All right, so if this is wavelength and we have C, the speed of light at all times, we need to isolate V by doing what? Say again? Dividing by wavelength. Good. Dividing by wavelength. So I like to usually set up my variables first and then show like, hey, this cancels. So great. V, speed of light, frequency, is equal to C over wavelength. If I set it up like that, and then I plug my numbers in, I'm less likely to put a number in the wrong place. And I think that's helpful. So 3 times 10 to the 8th, which is the speed of light, meters/seconds, so meters per second, over lambda, which is our wavelength we just calculated, so we're going to put that down there, 4.0 times 10 to the negative 7 meters. What units cancel? Meters, leaving us with what? Not just seconds. See that slash? We have per seconds left, or seconds to the negative 1. Or, baby, you don't, hertz, thank you, hertz me. So this is 7.5 times 10 to the negative, no, the positive. You guys hopefully are calculating this for me. I'm doing this in my head. 14, positive 14. Per second. Okay, so that is how fast this thing is traveling. And you can record this as per second like this, or seconds to -1, or hertz. Not hard, one equation. One down, one to go. Okay? So I need you to know how what each of these variables represent, how to take one variable to the appropriate units, and plug in as needed. How are we feeling right now? Math, right? Math, chemistry. I think you're like, I thought I signed up for chemistry. You did. It's got some math in it, though. Okay, so why is this important? We have to figure out how these scientists came to their understandings of the atomic model. Well, Bohr, this is something you wrote down on your scientific notes to the historical model. You may remember seeing some of those, the words are specifically quantized. And this model now is coming into play because it's now on your paper. I'm showing you where it is, how to use it. So what Bohr saw was that there were such things as glowing metals. And he was like, oh man, this metal, it glows bright orange. And this one glows when it's hot, when it's really hot, by the way. It's not just glowing like radioactive. It's glowing because it's hot. It's yellow, it's red, it's this color, it's this color. And then he would heat up gases, and the gases would glow like neon lights, pink, purple, blue. And you'd see all this, and it's like, why are these different colors coming off? And we figured it out. There are electrons that live in these orbits. So this is the nucleus in the very middle. There are electrons that live in the orbit right around the nucleus, the second orbit, the third orbit, the fourth orbit, and so forth. And he said that when electrons get excited, they move around. Well, they can't sustain that excitement for very long. And so they jump from, let's say, energy level 1. They jump all the way out here. They're very, very excited. They have a lot of energy. Well, then they fall back down. And when they fall down, they must release energy. And that energy that they release is in a specific wavelength that we can see, visible light. And so that energy is what we are correlating to visible light. We can actually calculate the energy of the wavelengths of light. And it's related to just electrons jumping around in energy levels. So that's why we were going to start to quantify the energy of the electron, as well as the light that it's giving off when it releases energy. We're going to do 2 labs with this. They're very cool. So what Bohr said was, well, this particular model I'm looking at is hydrogen, and it only makes 4 different colors. 4 different colors are going to be coming from different transitions. So like maybe transitioning from, let's show you the picture actually here. Transitioning from this energy level down here, this one down here, this one down here, and a farther one down here. Okay, so look at the blue paper. Is there an extra one? So how do you use this to figure out like wavelengths and energy? So let's look at the transition from energy level 3. So I see n equals 3, and it's going to transition down to n equals 1. What does that line say? 103. 103 what? Say again? Do you see the units on the very top of this little chart? Nanometers. So I could say, all right, guys, the electron has transitioned from n equals 3 to n equals 1. I could say, what's the frequency, what's the wavelength, and what's the energy? So can you guys tell me right now what the wavelength is? You just told me. 103 nanometers. Okay? And if I asked for the frequency, what equation would you use? Speed of light one, c is equal to lambda times frequency, and you'd be plugging this in here, but what would you do that first? Change it to meters, right? You'd have to change that to meters first and then put it in there. And then I could also say, okay, let's calculate the energy of that particular wave, and that's where we're going to use this equation. We'll get there in just a second. Okay? So this is how these 2 things are connected. You okay with that? Okay, let's look a little bit more. So the term quantized is just telling us that they have energy. They have a specific amount of energy, and that's why we can calculate these specific numbers. And then spectral lines. I didn't bring the spectroscope out. We're going to do a lab with spectroscopes tomorrow. Have you guys ever seen the Pink Floyd image where it's like the light shines through the prism and it breaks out into the rainbow? That's actually called spectrofilm or a prism. And it takes light and it separates it into all of its wavelengths. And that is something we can do in class. We'll do it with many, many, many forms of light. We'll have lots of different wavelengths that we can see. Okay, so I told you how he did it. These are the notes that give you some more information on how do we get these electrons to an excited state. Okay, so read through, write down some of that, and I'll talk about it. we are going to light things on fire and shock the crap out of some electrons to get them excited so they can catch the light. Okay? It's for the sake of education. Okay? No electrons were harmed in this. I'll go over this in just a moment. So these electrons, they live on the outside, the electron cloud around the nucleus. And different people have called these areas different things. Bohr specifically calls them orbits. Those electrons, they live in orbits. And so orbits, they're either close to the nucleus or far away from the nucleus, and the electrons can move between these set pathways, these orbits. And if the only way they can move between them is if they are excited. And you can excite them with either shocking them with electricity or pretty much heating them up, like setting them on fire. And so we will do that later on. But whenever they get to the top, that's called the excited state. And so the electrons in the excited state, they're very unstable. And so if they're unstable, they must fall back down. And when they fall back down, they release that excitement. They release that energy. And if it's in that narrow spectrum, we can see that energy. Sometimes it's out of our seeable range, so it's not invisible. It's like UV or it's an IR. But another way to excite the electron is to shine light on it. And that's what you see here. A photon is being shown on this particular atom, and the electron is bouncing out to a high energy state. So that's what we see. You can see it through those like particulate matters like this. And then after they fall back down, we call that ground state. So I have that here, yeah. So the terms excited state and ground state, you should know excited state and ground state. Ground state is closer to mom, the nucleus. Excited state is out in no man's land. And then as they release light, sometimes we can actually see it. And so the releasing of light waves is also termed photons. Okay, are we okay here? Are you making some connections? Okay, we're going to work on, well, let me see. I had one more. Okay, we'll get on that in just a second. So this is what we talked about yesterday. I tried to draw my little spectra, black emission spectra, and then the continuous spectra. So different atoms, we know they have different number of electrons, right? Hydrogen has 1 electron. Well, hydrogen, what Bohr saw, was it actually can jump around to 4 different energy levels. It makes 4 different lines. Can you imagine what something like, I don't know, oxygen, chlorine's got 17 electrons. It probably can make 4 times 17. It can probably make quite a few lines. And those lines are these emission lines that you see here on this black background. And we're going to work with that a lot more in our lab tomorrow. But another term for that is the bright line spectra. Where are these lines coming from? Where are these emissions of energy coming from? Anybody? Lines come from energy being released. And how is the energy released? Right, so they're falling from excited state to ground state. Okay, so the lines are coming from the energy that's being released, which is coming from electrons falling. And if I say electrons falling, you get what I'm saying, falling from excited to ground. Okay, so that's what I wanted to make that connection, but it's hard because you can't see the atom, and you have to only see the results of what the atom is doing, and that's what this is. You can see these lights. And this down here, this is maybe a little hard to see. There's a line here at 410, at 433, at 486, and at 656. Those are the emission lines of hydrogen. So every single atom has a different bright line spectrum. And we also call it the atomic fingerprint. Because just like you guys, everybody has different fingerprint. That's kind of calling your identity. It's a special print for you. We call it the atomic fingerprint because this emission spectrum is different for every single atom, every different element. Okay. So we're going to work with the energy part of this in just a minute. Pass back those papers I handed out if you haven't already. Take a break from me for a couple minutes. Maybe let's do about 10 minutes and see where we are. The first picture has a chart with it. Here, yeah, we might need that again. The first picture has some images with different wavelengths of light. And it says to color, don't color. Okay, I want you guys to practice what this talks right now before we look at some new stuff. You'll see a spectroscope in this next image, and I can pull the images up here. Let's shoot to get through at least number 11. Okay, and then we're going to get a good model for you after we talk about energy. If you work with somebody next to you, say 15. Okay, move around for me too. You can write on this. This is yours. Write on this. Is this an emergency? And if you can't see it, it does say 10 to the 8th on the speed. It does say 10 to the 8th. Yeah. No, don't call it. I know you want to, Scott, but.
Purple one. Oh, that's 3. I'm kidding.
You just want to see what the gas is starting to look like. We don't have to know what it's starting on the well. All it is in this tube, there's some gas capture. And there's like electrodes on the other side. So when you stick it in this high voltage system and turn it on, it like basically electrically argon atoms, and it makes their electrons get excited, and then immediately electrons fall back down, and it looks like that. So what we will see tomorrow is we will take a spectrum of prism basically over this. We'll see line, but not continuous. So we have gaps between it, and we can actually look on this little measuring device and calculate its wavelength and its frequency. Okay, so that's what and we have to keep it hot. Sometimes it gets very hot. That hot, but I get on the water and very hot. So I'm just setting electricity, that's it. Okay. So let's see how we are doing so far. And we're going to calculate energy. I always feel like I move too fast on this, but we're feeling okay. Moving on. So much to calculate energy with me. There you go. So why, looking at number 3, why does it say reds instead of red? I'll just call you guys out here. Abby, why do you think it says red instead of reds? I mean, reds instead of shades. Right, different shades mean different wavelengths of red, right? Good. Do all of them travel at the same speed? Nicole?
No. Well, yes.
Yes, they also travel at the speed of light. Looking at number 6. Which color has the longest wavelength, Melanie? Red has the longest wavelength. Nah, which has the shortest?
Violet.
Violet, good. And then C, reticence, that describes the relationship. Increasing the wavelength does what to the energy? Decreases the energy. Increasing the wavelength decreases the energy. Long and slow. Okay. Looking at number 8, list the spectral lines for the hydrogen color and the corresponding wavelength. These are the hydrogen gas spectra. You can see them on your paper as well. So what you can see is that near the 400s is kind of the violet-ish area, and near the 700s is the red area. So you could have listed some of those. And then boron has more electrons. Guess what? It's got more lines too because there's more available transitions, more electrons moving around. It means there's more lines on the spectra. And look at number 11. What color of light has the most energy on number 11? Violet. Okay, and we can see that because it's the shortest wavelength. Short things move faster. And you can see as well based off the energy they give you on the chart. Okay, so hold on to that for a moment. Let's talk about energy. Calculate with me. And I'm going to go back here. I'll come back to that. Okay, so energy. Energy is who's credited with this many times if you're credited with this. If you need to move back to where your notes are, or as long as you have your notes, make sure you're writing down examples with me because you will hate your life if you don't. Okay, I know this unit very well. I know that this is one where people have a struggle with because they don't write down notes. Okay, so the 2 equations we are using are on the board. You need to know how to manipulate them. All right, so Planck is one guy who's actually very important. There's a constant named after him, right? When there's a constant named after you, you have succeeded in life. And Planck's constant is right here, H 6.626 times 10 to the negative 34th joule seconds. Joule seconds is a big unit. It's a combined unit, derived unit. So he studied along with 4 hot glowing gases and solids and saw that with the frequency of light given off, there was a relationship with that with its energy. And he said it's a direct relationship. as the frequency of the wavelength went up, that meant the energy also went up. And so he made a correlation, and he actually came up with a constant that relates those two variables, and that's his constant. This does relate to Einstein's theory of relativity, because he deals with speed of light, he deals with relativity of time and everything. But Einstein, he's not a big player in chemistry, he's more of a bigger player in physics. But I do want to note for you, for specifically one multiple choice question on this test, that his equation brings together the speed of light, energy, and mass. We haven't talked about mass at all in this whole wavelength deal. The only time we've ever talked about mass is the fact that waves, meaning like the electromagnetic spectrum, has a particle nature to it, kind of that particle wave duality. And when I say particle, I mean has mass and volume. When I say wave, I mean it has a wavelength and frequency. So if it has either of those, then we call it. So if it has particle nature, it's dealing with matter. And if it has a wave nature, it's dealing with things, variables we've been talking about. So Einstein says that energy has mass, which is why in nuclear explosions there's a mass difference when the energy is given off, or a radioactive decay, there's a mass difference. But I just want to tell you that because there's like one choice question with that. Okay. So do you have your equation for the E? Oops, right here. You have this down. That's what we're going to work with. Okay, so we have a neon laser. Lasers give off a frequency of light, pulses, different pulses. So the helium neon laser emits a light with a wavelength of 633 nanometers. So label your givens, write down your givens, whatever you got to do. Wavelength is 633 nanometers. Question 1, what is the frequency? And I'll say question 2, what is the energy? So we can kind of knock them all out in one question together. So you guys tell me where to start on this first one. If I want you to solve for frequency first. Okay, first off, how about we choose the appropriate equation? The speed of light one is the appropriate one, right? So I'm actually going to write that down. Good job, Eli. Just so you don't forget. 3.00 times 10 to the 8 meters per second. Okay, so I've got my wavelength. I've got my speed of light, and I know I'm questioning the frequency. Now what's my actual first step? Right, I got to change those nanometers. I don't see nanometers in the speed of light, so I have to change. What is our conversion again? What goes on top? 1 meter and, right, 10 to the 9th, nano 9. Don't forget that. And that's going to allow for you to convert to meters. And if you're doing this, trying to figure out how to do this in your head, you're probably just going to go, all right, got to move the decimal back 9 decimals. Well, back 9 decimals just means that that is going to be 6.33 times 10 to the negative 7, because you're moving it back 7 and you're doing this. I always do scientific notation because this would be ridiculous to write in non-scientific notation. So 6.33 times 10 to the negative 7 meters is our wavelength. Okay, write down your speed of light equation. What do I do to manipulate this to solve for V? Divide by wavelength again. This is the same step as earlier. And so the wavelength cancels. So then V for frequency is equal to C over lambda, which is 3.00 times 10 to the 8 meters per second, over meters, we just calculated 6.33 times 10 to the negative 7th meters. Calculate in your calculator with appropriate parentheses. I'll make sure you guys are good with that calculator, because some of us on our unit test, which I'll get back at the end of class here, need some help with that calculator. James, you have it?
4.7393.
I'm gonna go 4.74 times 10 to the what? 14 units. It's not just seconds. Per second. So you can do seconds to -1. You can do like 1 over seconds like that, or you can go hertz. Either of those units will work for me. So that's just our frequency. I added to this question. I said I'll actually you guys to now actually solve for the energy of this laser. That's why you don't shine lasers in people's eyes. Okay, kill their cells. How do I figure out the energy of this? Use the other equation. So now we officially get to use Planck's constant. E is equal to hv. E is the energy that we're solving for. H is what again? -34 units. Joule seconds. Okay? Can't have like naked numbers running around here. This is the high school people. Okay, and then energy is going to be calculated with the frequency we just calculated, which is 4.74 times 10 to the 14th. And I prefer per seconds, and you'll see why here. So if I write this as per second, like /second, I can write it as under, second goes under the denominator or in the denominator. So that's what per second looks like if you're writing it as numerator denominator fraction. What happens to the units? Seconds cancels, and then it makes sense. What is the energy unit that we accept in the SI system? Joules. So this should be established in joules. Yay. Okay. Calculate and any takers? -19 joules. That doesn't seem like a lot of energy. Okay, so 3.14 times 10 to the -19 joules. We'll call it a lot of energy. That's energy of the laser that we just calculated the frequency of. And joules is our final unit. And sig figs 3. Yep, we're doing good on that on all accounts. Okay, so you have two equations. You can calculate three things. Try this one at the bottom. An FM radio station broadcasts the frequency of, what is that unit there? Megahertz. Okay, so this is megahertz. I want you to calculate the wavelength and the energy of that radio wave. And you have to go back to your King Henry, blah, 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 and calculate the megahertz. Person next to you. All right, what was our first step, guys? Maybe that you're still working on, but what are you doing right now? So, when I hear divide, but what are you doing with this? To normal hertz, right? Change it to normal hertz. So, 98.5 megahertz. We're going to convert it to just normal hertz. We want to get to normal hertz, which is just our frequency unit. And then megahertz is going to go on bottom, but what numbers go with these? Who's the bigger unit? Megahertz. Megatron. Okay, and then the other one? If we call hertz like the, so mega, King, Henry, died by drinking chocolate milk, and everything else. call it a base unit because it doesn't have a prefix. How many zeros away? 6. So that's 10 to the 6th hertz difference there. So then that would be 9.85 times 10 to the 7 hertz. Yeah, which is also per second. Okay, so that's our B. That's our frequency. Then what did you implement? You can actually go either way here. Who wants to do energy? Who wants to do wavelength? Who wants to do energy? Let's do wavelength. Wavelength wins. Okay, great. So if you're solving for wavelength, which equation? Speed of light 1. Good. C is equal to. Oh, okay. Wavelength times frequency. And solving for wavelength this time, so I'm going to divide by frequency. And then lambda is equal to C over V. So it's just generally, I like to plug in variables and then, solve for various variables and then plug them in. C is 3.00 times 10 to the 8th meters per second. Frequency is 9.85 times 10 to the 7th. And hertz, I'm not going to write hertz because I want the units to agree with each other. I'm going to write them as actually per second this time, /second. What unit should cancel? Second ones. And then that leaves us with meters. Is that a unit of length? Yep, specifically wavelength, yes. So who's got me here? Evan, what you got? Okay. 3.0, I'm listening to you. I can pour this in. Okay, ooh, that's a long wavelength. 5 meters. Okay, so basically, guys, that's 3 meters, right? Isn't that kind of what we said a wavelength of a radio wave was like earlier? A little taller than me, some of them. This is a pretty short wave, radio wave actually. So that's how long it is. We can't see it, but it's really long. And then how do I get energy? Well, I get into the second one. You're right. Perfect. E is equal to hv. What is h? 6.626 times 10 to the negative 34 units, joule seconds, right? They will haunt you people, okay? And then V is what we previously saw for up here. Plugging that one in down low again. 9.85 times 10 to the 7th per second. And that will give us just the unit of joules, because seconds will cancel, and a lovely number such as I know the suspense is killing you. 6.53 times 10 to the negative 26 joules. Yeah. All right, guys. All right, I don't want to kick a dead horse anymore. If you know how to do this, or you feel like I can successfully implant both these things into 2 different equations, yeah, put your thumbs up. And the other version of this was use the Bohr model. Can you look on the Bohr model and figure out your wavelength? Where I was like n equals 5 to n equals 2, it dropped down. Look there for the wavelength. That's basically the 3 varieties of this style of problem. So I have a couple more informational pieces, but I think that you guys get it. Who has PS5 with them? Or I can pull it up. We have PS5? Yes? Okay. So, hold on. I was going to do the PS5. Do me a favor. Under Model 3, it has the Bohr model. This is the part that is the part we've not heard much. Can you guys go through 18 and 19? Yeah, go through 18 and 19 before you move on to PS5.
Sorry, no.
Oh, no. I was going to start, finish up 19 here first, and then I'll show you what you guys can do on there. I was going to pull it up for you. 18 and 19.
I don't understand the
Okay, just saw that zoned out look there. Speaking of absorbing light.
You guys up there?
You're probably going to have to look at your blue sheet. For the number, for the color of light for that one, anyway. On number 19. They are referring to hydrogen. You can look above at the model 2 as well, but if you want the specific one, you can look there.
Oh.
You guys are making some good, I can hear your communication with each other. I think you're making some good conclusions. Let's finish this part together so that I can verify that you're okay. So you can see the energy level going from low to high here. So absorbing or releasing energy. Absorbing. Okay, so you should be able to use all these, like these terms, they're not interchangeable. There's like 3 terms for the same thing, okay? So if you're taking in energy, you're absorbing energy. So 18 should be absorbing because you're increasing to a higher excited state. Thank you, whoever that is there. These correlate to the hydrogen model, which is right above it. The hydrogen model, how many lines do they have on their little spectrum? The hydrogen. Look at the model 2. You see the one at the top one is 4 lines. Red, blue, green, blue, violet, and violet. You see those? Okay. Which is the longest wavelength? Red is the longest wavelength. Which of these is the longest wavelength? D. Okay. So I want you to make this correlation as we're going here, okay? So this one is the red. Okay. So this one is the red one, and it has the lowest drop, okay? That low drop correlates to a low what? Energy. Good. There's a low difference in energy between these 2 energy levels, so that's a low energy. So I'm going to just put decreasing energy or low energy. That correlates with a high wavelength. So are these directly or indirectly related? Do you see that they're opposites? Remember, directly means the same way, indirectly means opposite ways. Okay, so this is an indirect relationship. This is the red one. This one is the one that's dropping from n equals 3 to n equals 2. Yeah, okay. So, which do you think is the violet one? A, because it has, give me some characteristics. No, doesn't move with me. Okay, well, we're going to scooch over here. Look, what do you see here? Short wavelength. Okay, it's really, really small, so wavelength is short or low. Okay, what do you correlate that with here? So if it's passing through multiple energy levels, that's a large amount of energy that's being transitioned or changed. So that's going to be an increase in energy. And that's from n equals 5 to n equals 2. Okay? And that's what the little questions on the bottom are referring to. Label the picture n equals 5 and equals 2 and the corresponding light. So this one is violet. So then what would the rest of these be? What would this one be over here? This one would be which one? The blue-violet one, right? And then the lower one down here would be the blue-green. And you can see the energy is diminishing as we go, and the wavelength is increasing as we go. So this is reinforcing the whole indirect relationship between those two. On the bottom, it also gives you a couple things to denote. These electron transitions, are they absorbing or releasing energy in this case? These are all doing what? Releasing, because if you're dropping from a high energy state to a low energy state, that's releasing energy. So circle releasing. And as the electron moving from the electron moves from a higher energy state to a lower energy state, so that's correlating with B. And so is light absorbed or released here? Released. And that's only because, so we're saying light, because this energy falls in this narrow spectrum of where visible light exists. Okay, look at 20. Actually, I think we're good here, because some of this gets repetitive here. Okay, now you have PS5. I'll show you my PS5. You show me your PS5 here. Okay. PS5. PS5. Student packet. Oh, is this your nugget? Thanks. You're going to be working on PS5 for like 3 days, okay? And it's going to be a little bit at a time because I don't want you to. Okay, the reason I have you guys work on things a little bit at a time versus not long is because your brain makes neurological connections. Okay, that's why I assign a little bit at a time. So when you don't get overwhelmed, you can ask questions while it's fresh, and there's more. You have a higher likelihood of actually remembering these things. Okay, it's scientifically proven, or supported. On PS5, you have matching, which you know some of these terms now. The vocabulary here is very rich. It's very important to be able to say your vocabulary appropriately. Down here, you don't know how to do any of this mess yet. Don't even look at this, anything with electrons and FP, DFS, stuff like that. It's going to be solve these problems right here. So you're going to be doing this a couple times. You will love it by the end of it. We're all going to get tattoos of these equations, okay? So you're going to love them. And write your units, convert as needed, but work on these tonight. And then the next night, you'll actually be able to do the spectroscope one. It says energy, number 10, energy associated with the spectroscope. We're going to talk about spectroscopes tomorrow. That's actually what you measure light with. There's a table that has the ends in it, like we just talked about. And I filled out one of them, you're solving for the other ones. So pace yourself. This one's, it's like 20, maybe not quite 20 questions of this. And then the answers are at the bottom. They're a little, I think, goofed up, like in terms of orientation, like they're not spaced out appropriately on yours. Can't remember if I've uploaded this one, but I will. But it has the answers. I don't have the units on mine though. And you just need to show your work. Show your work always. Okay. So if you guys want to work, I'll leave it right here. 1, 2, you guys can see the rest. And I'm going to pass out your units. Actually, I can't now. I have to wait on how many people take tests. But I will pass out your unit 1 test tomorrow and plan on, if you did not do great, you will come in to be with me. Okay? Be Friday, and you'll know that tomorrow. Just because I can't pass out test yet, because I'm waiting on a couple of minutes. I will try to upload the grades tonight, then for the first time. Okay, so work for the last 10 minutes on PS5. You guys can leave these at your desk. Either way. Not yet. Start 10 minutes left in class. 7 minutes left in class. You want to start? I'll do start. Yeah. Yeah. Do not pack up early. That's when you get a detention because that's nonsense. We've already got class cut to the heel. Use your time. All right, Jasmine, do you have a calculator?